Hello and welcome back to the Raspberry Pi coding channel. This is part 8 of Humans versus AI. Now in this video we're going to do what I mentioned that we would do in the previous video, which is to refactor the code and to also fix no less than 7 minor issues that we do need to address before we wrap the code inside a machine learning training loop. As mentioned, as I've mentioned in other videos, I have a Patreon account. If you'd like to contribute to my work, this is where to do it, and I'd very much appreciate it. Thank you to those who do. And by doing so, you'll have access to the code, as you know, from previous videos, and early access to the videos. Thank you very much. Right, because of time, let's crack on. This is going to be quite a long one, because there's quite a bit to go through. So I'm going to be as quick and concise as I can, without losing the detail. So in previous videos, up to this point, we've written a single file. This is from the previous video 7. So what we've got is we've got a single file comprised of around 300 lines of code. There we go, 300 lines of code. And it's comprised of a series of global functions at the bottom, some of which are utilitarian in their nature and can be taken out into their own file. And then we have two classes. We have the player class and we have the game class, game app, which is how we get into using arcade. And then above that, we have the constants, which allow us to configure how the game is going to run. So the first part of this video is to refactor and basically get rid of this giant monolithic single file and split it out. This is essential and needs to be done because adding a machine learning training loop around this game will add code to the game, which we want to make as clear as possible so that we don't get confused with what is part of the training process and what is part of the game, etc. So we're going to clean it up. So the first thing we're going to do, open this back up again, is there are a series of files we're going to create. Firstly, we're going to look at main. So main is essentially the replacement for 6.py. It's the replacement for the entry point of the program. And if I just scroll down briefly before we get into the details, you'll see that it is now 178 lines long rather than 300 because we've separated out bits of the code into separate files. So as you can see by looking at main.py down at the bottom, we still have the entry code. So this is where the code starts. So we still run the code via main. It's still the entry point. This is all the same as it always has been. We create an instance of the game app class, we then run the setup, and then we start the game loop. And this is where we enter. So this is all exactly the same. Okay, so that's main. The first thing then you'll notice is we are missing the constants that were at the top. Unsurprisingly, they've been put in a file called constants.py, and you can see they are being imported here as part of the new app imports list of imports into main.py. So that's quite an easy refactor. If we go to constants, you'll find all of the familiar variables that we set to configure the game in the first instance. So that's that. The next thing we've done is we've pulled out some of those global methods. If we go down to on 6 again and go down to the bottom, we've got methods that are outside of our two classes. Here they are, they start here. Some of these are utilitarian, used in multiple places and don't specifically apply to a given game event. For example, set up energy points is specific to energy. Grid create texture is specific to grid. But distance, random position, and draw FPS are all generic functions that can be separated out. So we now have another import here, which is utils. And as you can see, sorry, my mouse keeps hiding. We've now got a utils file, and we're importing all of the methods from there. And if we go into utils, just here, you'll see the methods that I just mentioned. Distance, random position, and draw FPS. So all we've done is we've split out these methods into their own file and then imported them to keep things clean. And we now have a home for utility type methods, no longer polluting, in a sense, the main entry point file. And the last thing I did is I took out the player class from this, from 6.py, because it's quite useful to keep classes separate. It keeps the logic separate. It makes it easier to find a problem. So in addition to constants and utils, we now have a player file. The player file contains the player class. Player class, of course, contains all of the state associated with where we create the instance in the constructor. And then it has all of the methods that player class uses to handle that player instance. So that's just an extraction of the player class. Because players use some of the constants that we set up for the game, you'll see that we also import the constants file as well. Okay, so that's the refactoring essentially done and covered off. That's all we've done. We've just split things out into separate files. Okay, so I'll tick that off. So now we've got a number of 1, 2, 3, 4, 5, 6 other items to go through to kind of finish off this code and to make it ready for training. So the first one is snap to grid. If you remember, a few times, in fact, I've mentioned that I don't like the snap to grid code. It served a purpose to get it going, for us to talk about getting a basic game engine working quickly, but it isn't ideal and it's prone to error. So if I scroll up in file 6, so this was last video, for reference, we go to the update position method, which is, if you recall, the method where we update the player position in increments to create that animation, converging current X position onto the target X, and the same, of course, for Y. So that's the method that's run in the onUpdate method. If you recall, an onUpdate is run with every frame of the game loop. Now, at the bottom, not at the bottom, sorry, just above the bottom, we had the snap to target logic. And in here, we basically say, if the current position and the target position are very close together in X and Y, we basically snap them together. It's snap to grid. So what's the problem with that? Problem with that is the game has variable speed. When we train the game, we're not going to run the training loop on every single frame. It's inefficient because a lot of frames are just animating the player from A to B. No decision can be made whilst the player is in transit, so there's no point making a decision at every single frame. It's inefficient computationally and also might make it harder for the machine to learn. So we don't want to be able to make a decision between the frames anyway. So at the moment, this logic, given that we're going to sample frames in training, is probably going to break. Because as we say sample it every 10th of a frame, it's possible that we will miss the window for snapping to grid. Also, there's another way of missing the window. If a player's speed increases, which is eventually going to be something that might be possible with an upgrade, for example, the player could overshoot because step X or step Y are too big. They could overshoot this narrow 0.1 by 0.1 window. And if it does, then it's going to oscillate back and forth between the target, because it's going to overshoot and then go, oh, I need to go back because target is now on the other side. Oh, I overshoot again, and it's just going to keep doing this. And the player basically gets stuck. Not even just the AI, but the human player won't be able to do anything because you'll be forever in transit because you'll never snap to grid. Okay, so you can see the problem. Having this fixed small window isn't okay. So if we go back to main then, and we're going to look at update position, and I'll just search for it. Update position. It's a player class method, so we'll go into the player file. That should have just gone straight there. I forgot about that. If we go into update position, we'll now see the code is substantially different, and we'll just compare the two. So on file 6, we had very simple logic that snapped the two variables, current X, target X, current Y, target Y, together based on this window. If we go to main, if we go to player, sorry, we'll see the logic is substantially more complicated. It's this piece here. So running through what it's doing, we're basically saying if we overshoot the target, then we need to snap to the target. So it's a different logic. It says if step X is greater than or equal to the delta between target and current, then we're going to snap it only then. So it does mean if we overshoot, it's going to basically go back in that frame to the center of the grid. And then there's another, grid cell. Then there's another piece here, which is saying, or if it's very close, snap to the grid. And this extra bit, which is the same effectively as what we had before, is in case we get very close but don't quite pass the point. We don't want to wait for another frame to overshoot, so we snap to grid then as well. So that's the logic. If we overshoot, we snap to grid, or if we're very close, we snap to grid. That's what's now happening. You'll notice that we are snapping here in this block, and if that isn't true, if we haven't overshot, that's when we're incrementing. So we do the incrementing afterwards. So it's slightly different, but the principle is the same. We're moving current x or current y in the direction of the target, but we're only doing it if we're not already snapping to grid. So slightly different logic, but the same principle. Okay, so that explains that. We're no longer going to get the potential for an oscillating animation that gets us locked out. The next thing we're going to look at is the game over situation. There's two things that have changed here. The first one, if we go to main and we go to the game class, the first one is going to be in the fact that we've pulled out the game over drawing code into its own method to simplify. So if I go back to 6, I go to onDraw, you'll remember that when game over happens and game over equals true, we're rendering these text elements to the screen to say game over, player 1 wins. So what we're now doing is, instead of that, we've got the same code here, but we have said, okay, if game over is true, then draw game over, just to simplify the draw loop so it doesn't get too cluttered. So that's the next thing I did. So I just go down to the bottom of the class methods, you can see draw game over. It's more concise. I got rid of the comments because I think it's self-explanatory now. And there's a little bit of logic. That's the next thing to explain. The logic is we've accounted for the fact that a draw might happen, which we hadn't done before. So it is possible that all of the energy points in the game might be consumed by the players, but no one player has reached the end score they need to reach to win. Under those conditions, we need to have a draw state. So we've now got the notion of if the winner object isn't populated, so if it's none, if it doesn't exist, then the else statement will run in this case. And instead of plotting out the player has won, it'll plot out nobody wins. Game over, nobody wins instead. So that's what that else statement is doing. If there is a winner object, however, this will run as it was before. It'll plot the player 1 has won, for example. So that's the change. So the question then is, okay, so where's the logic for managing the winner object? So if we go to on update. So on update is, as you know, is where logic for the game on each frame will be changed. And if we go to file 6 and look at the same section for reference, on update, there it is, it's a lot smaller. On update, in terms of the pertinent part, is here. We're looking at whether a player's energy is exceeding or is equal to the energy to win score. If it is, then we end the game. Game over equals true, which terminates the loop up here. And the winning player is assigned to the winner object just here. Okay, that's what it was before. It's a bit more complicated now. This code is all the same. All of this still exists, but then we've got a bit beneath it to handle the condition that we've run out of energy points and we have to decide who's won based on the number of points accrued by all of the players. And if there is no clear winner, then nobody wins. So let's go now to main, see this new logic. The new logic is this section here. So what it's doing is it's saying, so if the map has run out of energy points because the energy points list has a length of 0, the game must end. So we're going to terminate the game. That's still going to happen. We then look at how many energy has been collected for the players, and we take the max of it. So we're saying who's got the highest score. And then the other thing is there might be more than one of those. So the highest score is max energy, and then top players, we look at who in the list of players has the max energy. If there's only one, then we have a winner. But if there's more than one, which means more than one player has the max energy score, then we have a draw. And that's where we set winner to none. So in the on update loop, at a frame where the energy points have been depleted, we terminate the game, we see what the max energy is, we look for the top players who have the max energy, and if there is more than one of them, we are going to set the winner to none, and therefore we get a different screen to say that nobody's the winner. So that's another thing that we've changed. Right, on to the fourth thing. So this is a really minor change, actually, and very easy to explain. It's actually an oversight on my part. This is very quick. In the previous file, if we go to the draw function, you'll see that we're drawing the energy text that we see in the top left-hand corner. This is the scoreboard, basically. we're drawing it by making use of the player loop here. So we're drawing the players, this is the player circles, and in the same loop we're drawing the energy text. This seems convenient, but what it occasionally results in is the player can sit on top of the scoreboard for some of the players. So it can render the order, depending on the order of rendering of the players versus the order of rendering for the energy text, you actually can get a different order, and therefore the player can sit on top of the scoreboard. Some of the players can. So to solve that problem, to make sure they're distinctly after, to make sure that the scoreboard is plotted always after all of the players have been rendered, a very simple change is to simply pull it out of that loop for the rendering of the scoreboard and make sure it is always rendered on top, so at the end, after the players have all been rendered. So it fixes a minor bug that I haven't shown you, you haven't seen it, but I assure you it did exist. So we've just simply separated them out into their own loop. So I just wanted to make a note of that. Okay, that's 4 things done. The 5th is press key to exit. Yes. So if the game over state is true, so if we have concluded and the game has stopped, what happens is the onUpdate loop terminates. So the game state is not moving forwards anymore, but the actual terminal and indeed the window stays locked because the game hasn't actually exited, the code hasn't exited. So what we now have is an additional bit of logic in the on key press, which will say, okay, when a key is pressed, if game over state is true, then close the game, and this will exit the game. It's very similar to exit brackets. This will exit the game. So there's the additional logic, basically, so that when you're playing the game, you get to the termination condition and you press another key, everything actually ends now instead of just hanging. Right, we're nearly there. Thank you for bearing with me. The very last thing we need to do then to prepare is, and this is the most important one I've left till last really, it's the checks. So if we go to setup up here, I've now got a new method called check. Now this is really important ahead of machine learning. So we're getting to something quite tangible here. When we do machine learning, we're going to be playing with the settings a lot to see how the machine learns, to see what conditions work the best. And we currently don't really have any protection against inaccurate or incorrect configuration, where the configuration just doesn't quite make sense. And so you can end up training the model on a setup which is weird, for example. So what this function does is it has 4 checks that I could think of off the top of my head that will help protect us from running a large training job with a poorly configured game. So let's have a quick look at each one and then we'll run it and I'll show the game running basically just for completion. The first one is quite an obvious one. It checks that you haven't set the energy points too low, where the energy to win is higher, or you've not set the energy to win too high with the energy points too low. So what can happen is, if you're messing around with the settings, is you can actually reduce the energy points as you're trying to get the machine to train better, because it's easier to train on fewer energy points, and not change the energy to win configuration, which means the energy to win is too high and the player will never be able to win the game. Under those conditions, that's very poor for training, and therefore, if you didn't notice, it would still do it. It would in each loop, but it would never end the game. So this is a great way of checking that, and the game will be exited if that condition is met. The next one is check the player's minimum distance is not too small. So it's just to make sure that the players can't accidentally be sitting on top of each other or very close. So this is basically saying the player min distance has to be 2 or greater, and just to check you've not made a silly mistake there. This one is to check the player's minimum distance is not too large. What can happen is if the player's minimum distance parameter is too big, for example, you've not changed it, but you've made the grid a lot smaller, again in the interest of helping training, what can happen is that the algorithm simply can't find locations that satisfy the condition of player min distance. And as such, the game will basically loop indefinitely as it tries to find places for the players to go. Because if you recall, when it puts players on the grid, it's doing it randomly, checks if they're too close, and then does it again. The startup of the game can just loop indefinitely if this isn't checked. So the condition I've set up here is that the player min distance must be greater than the grid size, the average dimension of the grid in X and Y. That's calculating the average dimension, times by 2/3 as a rough guess. So to say that they can't be any further away than that. Otherwise, you're going to start having real trouble. In fact, you still might have trouble at that large. If you've got enough players, it might be impossible for the machine to find places to put them when you've got multiple players. But this is a good way to protect us against the most obvious condition of having it far too big for the grid. And the last one is check energy density is reasonable. So energy points versus the size of the grid. So this is just a way of saying, just make sure that there aren't too many energy points. We haven't changed the number of energy points or changed the grid size out of proportion with each other. So what it's saying is if the energy points are greater than a quarter of the number of grid cells, then we need to throw an error. And we'll just do that now. Actually, we'll just run this to check it works first, and then I'll configure the game incorrectly just to demonstrate the problem. Okay, so here we've got it on a very small grid just for fun with lots of players. I'm green. I've set it so that I only have to select or collect one energy to win. So if I do that, there we go, player one has won. Okay, that works. Now let's do something daft. Let's go to constants and let's make sure we have far too many energy points for the size of the grid. So energy points is going to equal, let's go crazy and say 200. Okay, the grid is only 100 in size actually, so let's say 100. They'll both break, but let's do it at least a bit more realistically. Now if I play, you probably can't see it easily at the bottom, but at the bottom of the screen, which might be cut off in the video, it says energy point density seems too high with 100 energy points populating 100 available grid tiles. And that's coming from here. Energy point density seems too high, blah, blah, blah. Okay, so there are the checks that we've now put in place. So I'll just undo that change. There we go. Okay, so that draws to an end this quite lengthy video on refactoring and preparing our game for machine learning training. We've now got a quite optimized rendering engine that has been refactored into a sensible format. We've got some protection in place to stop incorrect configuration up to a point. I'm sure I've missed something. We've got automated random sampling for the position of energy and the players, and the coloring now works correctly. We've solved the problem of snapping to grid. We're allowed the option of now drawing, which is important. And that's pretty much it. I think it's worth pausing now and saying we're at the exciting part. We've got the basic of basic games here, but it is now enough. It's in a good kind of configuration, and we're ready now to wrap this in a machine learning training loop. So in the next video, we're going to start that process. You'll see us creating additional functions. One of them is an important one, or actually they're all important, but easy to understand. One of them is going to be to take the game state and flatten it down, ready to go into a machine learning model. So the game state is going to be things like where the energy is relative to the player, for example, that sort of thing. So we're going to create what you might consider to be helper functions within the main function. They're going to be functions that allow the game loop to tap into them so that the training loop can tap into them so that the training loop can interface with the game logic without rendering the game necessarily. It's very important to do that. We need to be able to use the functions in here to make the game work without running the whole game. And that's part of how this all works. Anyway, I'll talk about that properly when we get to it. So thank you for joining me, and I look forward to seeing you in the next video where we start preparing for the machine learning modeling.